proteins must have some kind of signal. Can't be the same signal. It's got to be a different signal, right? So we'll talk about some of those other signals later. We're together. Now, do you have a question, Carl?
Yes. Number 4 says note 2 main types of secondary structures on proteins.
Did you say 2? That's a mistake, so it should be 3. So what are the 3 types of secondary structure in proteins?
Alpha helix, beta sheet,
beta sheet, beta term. Okay, so make that correction on the what you should know. Now again, you're gonna start putting up amino acids on the board. So you gotta start memorizing these amino acids.
Do we need to know the molecular structure of each amino acid?
You need to know the structure.
Okay.
And you need to know the 1 and 3 letter abbreviations, and you need to be able to characterize the R group. So if I ask you whether the R group is polar, non-polar, you should be able to say that. If I ask you whether it's basic or acidic, you should be able to say that. Okay. If I ask you whether it's a hydrocarbon, you should know that, and we're going to talk about some amino acids that have oxyl groups in the R group. If I ask you whether it's a hydroxylated amino acid, you will answer that at some point. Okay. Number 2, characterize the mitochondrial protein signal sequence. CJ, do that for me right quick. Characterize the mitochondrial protein signal sequence. We just did that, sir. Were you listening? I wasn't. You were not. Carlos, do that for me right quick. You know what? This is too much for me. We just did this, didn't we? Was I done? Were you here? Did we say something about an empipathic helix?
Oh.
Well, what did we say?
That the empipathic does not give it is polar or non-polar.
So, yeah. All right. So if you find an empipathic helix at the N-terminus of a polypeptide chain, that is the mitochondrial signal sequence. Okay? And so when I say characterize it, I want you to say that it's a helical segment of the polypeptide chain at the N-terminus that's empipathic. You say that means that it has polar amino acids on one side, non-polar amino acids on the other. Now, you might further say that the specific polar amino acids carry a positive charge. They're basic amino acids on one side. You with me? That's what I mean by characterize. Devon.
Not all acids, because there's substances like preventing different potencies.
I can't hear you.
That they preventing different potencies.
So what about preventing it from folding?
What's on the first?
So let's hold off. That's getting into a little bit too much detail. But the one thing that I want you to remember is that one of these proteins is HSP70, right? And so what we are saying is that we have a conundrum with respect to HSP70. In some cases, it assists proteins in folding. In other cases, it prevents them from unfolding. And so at some point, we want to come back and answer that question. How does a protein work in 2 sort of diametrically opposed ways? All right? So now the point that we made is that a number of proteins actually become associated with the polypeptide chain that actually prevent it from folding. So we might come back and look at that in more detail later. Yes. A, B, and C under 8? 8, B, and C. Okay, 8, B, and C. So what role does the signal recognition protein play in attaching the mitochondrial signal sequence to the receptor? And so that's just, I may be asking for more than what I want here, but what would be your answer? What's the simple answer? Did you get a copy of what you said? So we're looking at 8B. So what role we said that there was a protein that recognized a signal sequence, right? That one of these proteins that's bound to the nascent polypeptide recognizes the signal sequence. And so B says, what role does this protein play in attaching the mitochondrial signal sequence to the receptors? One.
It'll lead the polypeptide to its destination.
Just, and basically all we're saying right now is that it just simply hands it over. It hands it over, right? And once it hands it over, it actually detaches because it's done its job. You with me on this?
Wait, so it hands what over?
So Brendan says it hands what over? It hands the amphipathic helix over, and therefore it's handing the nascent mitochondrial protein. Now, why do we call this protein a precursor? We keep calling it a precursor.
It has been translated.
What you say?
Has been translated.
No, we've already translated it. So we're going to further modify this protein once we get it inside the mitochondria. We just haven't gotten there. And then we have the final mature protein. Okay? So let me just tell you what we're going to do just in advance. We're going to cut the signal sequence off. We're going to cut the signal sequence off when we get it in the mitochondria. Why would we do that?
We got it to the
What'd you say?
destination.
You are related to where its destination is when you for it.
There is no need. It has served its function, right? It got us to where we wanted to go. Clip it off. We don't need it for the functionality of this protein once we fold the protein in the mitochondria. Now, once you get the protein in the mitochondria, again, just giving you a glimpse of where we're going, we're going to fold it into a three-dimensional structure. And that's going to be its functional structure. It will not have the signal sequence on it. We will have cut it off. And now we have the finally mature form of this protein. It's no longer a precursor protein. It is the mature form of the protein. You with me on that? Okay, now Brandon, you asked about 8BN. So C says, what is the next step after the attachment of the mitochondrial signal sequence to TOM? Can you help me with this, sir? What are you doing online here?
I'm sorry.
Oh, this is good.
What happens to this protein after signal sequence?
What's the next step? I mean, I just put these things on the board. We actually talked about 2 steps involved.
You go. There's another signal sequence that goes to translocase on the inner membrane because you've already gone to the outer membrane. Now there's another membrane that you need to cross.
So I said, once we attach to Tom, we're now going to detach from Tom and attach to who?
Tim.
Tim. That's all I'm asking. Okay? This is, I just need you to, okay? And so once we get to Tim, what's sort of pushing the protein in, or driving the protein in? What? The membrane potential. Now, does this make sense to us? So what is the membrane potential? Is it, what's characteristic of the matrix side of the membrane? What sort of, what charge? On the matrix side? Negative? On the inner membrane side? So how does this work to drive the signal sequence into the matrix? So positive is going to push it away, negative is going to attract it, right? So the membrane potential across the inner membrane is going to pull the signal sequence into the matrix. You with me on that? And so we'll finish this up on Friday. Now, is there another question about what you should know about the last lecture? Now, when you come in on Friday, I might give a pop quiz just for you in your honor. Okay? Because you kept me from doing it when I wanted to do it before. Okay?
Number 1, we asked about how does it differ?
All right, so number 1 asks, how does synthesis of mitochondrial protein differ from the way that we had synthesized other proteins on a cytosolic polycell? Let me hear from somebody else. Got all the answers, sir. How does, I mean, what's a major difference? Darius, I know you know the answer. What's the major difference between the picture that we drew of the synthesis of a mitochondrial precursor protein and just some other protein that we're making that we've already described on cytosolic polycell? Now, that should just jump out at you.
Is it because the protein is cold?
So that's it. Mitochondrial precursor protein does not fold. Okay? The picture that we drew before was that folding was co-translational. Took place at the same time that we were making a protein. Now, are we straight on this? Any other questions about what you should know about the last lecture? Now, again, we might expect a 5-minute pop quiz because we know everything on this. Now, we will have a quiz next week on the 3 preceding lectures. And so that quiz will be worth 24 points. I'm getting tired of giving these bonuses and nobody can take advantage of it. Okay? So one day next week could be Wednesday. Okay, I'm not sure. I'll let you know on Friday. We're going to have quiz number 3. Okay? It's not a pop quiz. It's a regular quiz. Now, I missed you at the department seminar yesterday. I gave you all your own personal invitations, and only 2 people showed up. It was a wonderful seminar. The guy talked about phagocytosis. Beautiful story. So I hope we'll get a chance to talk about it this semester. But he runs a program at Dartmouth that allows students to do research in the summer. 3 of our students actually did research last summer. 3 of them actually talked about their research and introduced it. And he gave really a very interesting talk. Okay? So he was around all day to talk to students who might be interested in going to Dartmouth to do research this summer. So you ought to look for opportunities like that. But again, I am inviting you to these department seminars. I'm also inviting you to senior seminars. Don't show up for that either. Okay, so we're going to review the exam today. Okay? So, I have something else for you. I have a gift for you. I have problem set 3. I know you've been waiting. Okay? It's really got some nice things in it. So there are 13 questions.
You didn't have to.
And you got 2 weeks. So that means you ought to be doing 1 question per day. Some of the questions are fairly easy, other questions are a bit more challenging. You need to get started on it today. Right? So it's coming around. And if you have questions about some of these things, come in and talk to me or talk to Sam about them. Okay? So at this point, I'm giving hints. All right? So if you have a real problem, just say, look, I can't seem to figure out how to do problem 3. Can you help me with it? All right, so coming around is problem set 3. You've got 2 weeks to do it. And I need you to write your answers thoroughly, and so I can read them if you don't use a computer. There's some good things, there's some good questions here. Okay, now who doesn't have a copy of the exam? Everybody should have an answer sheet. Now, I don't know why I have to keep saying to you that when we review the exam, that you need to bring your exams to the class. Don't give this back to me. Now, this is copied on both sides. I need you to come down and get it. Who else needs a copy of the exam? So
This wasn't the last exam we took.
You need a copy of the exam?
Dr. Haynes, this isn't the exam we just took.
This is not the exam?
This was from 2018.
How did I do this? I just copied this. This is not a good sign. So give me this copy back. Okay. So
Y'all are already here?
Those exams that I just passed out, wrong exam, my apologies. What you're going to have to do is just sit next to someone who has a copy of the exam. Again, if you don't have any questions about this, I'm going to run right through this and continue my lecture. Okay? So now you've had opportunity to look at this. And so here we go. Here we go. All right, so we're looking at copies of exam number 2. Exam number 2. We're still looking for our exam. Okay, questions about number 1. Number 2. You have a question about number 1. Okay, so what is the question about number 1? So now what I said, okay, so let me hear a question. How did I calculate? Did anybody do this calculation and get what I got? You got it yet? So what I did basically was, so the formula that we use is S equals 4dt to the 1/2 power. Is that right? You with me on this? Now, if you didn't use the right formula, I can't help you. So when I use that formula, so I ask you how far a lipid diffuses in 1 minute and 40 seconds. And so the equation, let me just go ahead and do this. The equation is 4 times 10 to the minus 8 centimeters squared per second times 1 minute and 40 seconds, which is 100 seconds. You with me on that? I multiplied 100 times 4, and I got 400 times 10 to the minus 8. I then took the square root of that, and I got 20 times 10 to the minus 4. That's in centimeters. I asked you in micrometers. So I just did my usual little conversion, centimeters to micrometers, and I come out with 20. So the relationship between centimeters and micrometers is 10 to the 4. Yes, sir. I can't hear you. Somebody help me out with the formula.
4dt.
Square root of
Yes.
4dt.
Is equal to what?
Square root of 4
The
dt.
square root of 4dt. 4dt to the 1/2 power. Again, I don't know why there should be a problem with that. All right, that's number 1. 2. Yes, sir.
Addition of number 2, give the answers E, but micrometers and millimeters, there shouldn't be.
I'm sorry, there should be what?
Submission, we're going from micrometers to nanometers, so shouldn't that be?
So that's, what's the difference between micrometers and nanometers?
10 to the negative 9.
That's the difference. Now, again, I've done this, and I actually did it with the student in my office yesterday, and we still, I think we got the same thing. Did anybody else get B? You got what? You got A. That's way, you got 2,300. I think you're going in the wrong direction. Yes, sir.
But you're going from a bigger to
I think I left my scan.
Because you went from kilometers to
So,
meters.
that's a good point.
Yeah, that's
You know, maybe have I done this wrong?
You shouldn't.
Let's point this right quick. You know, this happens sometimes, okay? This happens. So, I don't understand this. All right, so we're going to go, let's do this really quick. 2.3 micrometers. 2.3 micrometers. And so we're going to use my simple formula for making this conversion. So we want to go from micrometers, so I'm going to multiply this with 1 micrometer in the denominator and the corresponding number of nanometers in the numerator. Is that right? So now 1 micrometer is, this is a smaller unit. So we know that 1 nanometer is 10 to the minus 9th, 1 micrometer is 10 to the minus 6. This is the smaller unit, so this difference of 10 to the minus 3 or 10 to the 3 has to be 10 to the 3. Looks like I have a mistake here. So this would be 10 to the 3. We straight on that? All right. So now we multiply this, we get 2.3 times 10 to the 3rd nanometers. And it looks like my key is off. And so that's equal to 2,300, right? Is that right? This is why we have these sessions, right? So the answer to number B is actually A. Now, if you have B, you lose. If you have A, you gain. Right? It's a very simple problem. I don't know how I screwed it up.
Right, so you lose points.
Yes, this is a game that we play. Do I give you points? We're trying to get it. You know what we're trying to do in here? We're trying to arrive at truth. You know what I'm talking about? Truth. There is only one truth. This is not fake news. Okay? All right, so A is the answer for 2. I need you guys. This is what? Carlos.
So if you had it right on the scan form first, and that's the wrong answer, you seem to lose ones.
Did you hear what I just said? Is there a problem with what I just said?
I'm just confused.
So if you have A, do Do you have A? All right.
No, we have B.
All right, I know what you have. I'm not talking to Carlos. What do you have on your Scantron?
On my Scantron, I have B.
B. What did I just say about B?
It's wrong.
That's the wrong answer. A is the correct answer. Yes, sir.
Okay, I got it right, but like that's the way you taught it though. You know,
I'm sorry.
that's like when you taught it, you were telling us it was to the -3 though.
Yeah, you told us.
That's how you taught it to us.
We
What are you saying to me,
You know, I'm
sir?
saying in our notes when we were teaching it to you,
for a reason.
we chose B.
That's how we were.
Yeah, I chose A.
How could I ever say something like that?
That's what you
That's
said.
I must be absolutely delirious if I say
I
that.
can show you in the notes.
You got to show me that in the notes. You got to show me that in the notes. Now, if you show me that in the notes, I'll give you credit for B. Okay? So I can't imagine that I put something like that on the board. Is there somebody else who would say that? You would say,
I got it. Just because I looked at it, I'm like, I don't make
now
sense.
just because you put B doesn't mean that I put it on the board. Okay, so let's continue to deliberate on that. But right now, if you have A, you get an additional two points. Okay? My apologies about that. So A is correct.
You just circled the answer.
Yeah, just circle that on your answer sheet and give it back to me at the end of when we finish this. Questions about number 3, number 4, number 5, number 6.
Yeah.
Now, do we just, so what is the problem with number 6? So cell type X is spherical and has a diameter, so also how much larger? So there's a simple way of doing this, right? So how much larger is the S surface to volume ratio of one cell over the other? What did we reduce that to? 3 over R for each one, right? And so you could do that. There's actually, you could even simplify that further, right? So if you divide 3 over R by 3 over R, what do you get? What do you get? If you divide 3 over R by 3 over R. So we can simplify this even further. What do you get? Now these R's are obviously different, so you can't cancel them out.
You get R over R.
So that's actually an even greater simplification. Okay? But now if you do 3 over R for each one of them, you should come out with this answer, or an answer that's close to it. Now again, so some students said to me that they got answers, they may not have gotten exactly 160. So who worked that problem? What sort of answer did you get? What answer did you get? 161. All right, Jeff, what did you get for this problem? You don't remember? Did somebody else work it?
I did.
What did you get?
I got 161.
161. What did you get, Jeff? 161. Anybody else? What did you get?
Have 1.6.
Wow.
Something.
Okay. All right. What I need you to do, because I can't keep doing this math in here, just talk with one of the persons who actually got it correct. Okay? So all we're doing is dividing 3 over R. We're calculating 3 over R for one cell, 3 over R for another cell, and dividing the one with the largest by the one with the smaller surface to volume ratio. All right, 7. 7? Is there questions about this? 8. 9. 10. 11. 12. Well, all right, let's see what you got. Another one of these math equations. Now, we did this in my office yesterday, and we got a number 0.010, maybe 18. But it certainly was very close to 0.01023. And this is a problem that you got to do a number of things with. So I always start my calculations with a 1 molar solution, 1,000 milliliters of a 1 molar solution. Okay? And once I do 1,000 milliliters of a 1 molar solution, I might convert that to 1,000 milliliters of a 1 micromolar. So here you're trying to figure out how much to add to make up 25 mils of a 5.5 micromolar solution. And so I've given you the atomic weights of potassium and the atomic weight of chloride, and what you're going to do is add those to get how much you put in 1,000 mils to make a 1 mole solution to begin with. Are we straight on that? Okay, so now if I do this for 1 molar and I go down to micromolar, I'm going to divide that by 10 to the 6. So if I divide the amount by 10 to the 6, I know how to make up a 1 micromolar solution, 1,000 mils of that. Okay? And if I multiply it times 5.5, I know how to make up a 5.5 micromolar solution, 1,000 mils of it. And now all I have to do is convert to 25 mils. So I might convert it to 1 mil first. So if we have 1,000 mils, I'm going to divide this by 1,000, and then I'm at 1 mil. And if I now just multiply it times 25, I should be at what I need to make up 25 mils of 5.5 micromolar potassium chloride. Yes?
Could you like write it on the board like you did for the other problem?
No. I just said that. Why don't you record this? Yes?
I am.
So I got the same numbers, but I get 1.03.
So you keep going, there's something that's you're going in the wrong direction in some of your calculations. So your numbers, so you have 1. So you are 1,000 off from this number. So you saying, I'm sorry, you have 1.
I have 1.023 to the -6.
That's way off. So if I converted this to scientific notation, it would be 1.023 times 10 to the minus 2. Right? So you are 4 magnitudes off. And I don't know where the 4. So, why don't you come by my office? Just make it a point that we can go through some of this stuff. Okay? All right, 13. 14. 15. Now, Thomas, the reason I don't go through this is that, somebody might be able to come up and do what I did in a much simpler way. Okay? Just in one step. Right? I just was trying to go through it logically. Right? So we're looking at 14. All right, which of the following statements containing superoxide is accurate? Let's go through this very quickly. So one says that superoxide is formed by oxidation of an oxygen molecule. Is that correct? Superoxide is formed by oxidation. Is that correct?
No, it's
Why
an
is that
anion.
not correct?
It's an anion, so therefore it
It's
gains
formed by
electrons.
what? Reduction. Okay, we add an electron to it. 2 says that obligate anaerobes are not protected from damage by superoxide. What about that?
Correct.
And that's why they're obligate anaerobes, right? If you put them in oxygen, you're going to kill them because they can't protect themselves from oxygen-free radicals. All right, 3 says that organisms that utilize oxygen to produce ATP are protected from superoxide damage by specific enzymes. What about that? That's true, and one of the enzymes that we mentioned was what? Superoxide dismutase. All right, 4 says that superoxide is an oxygen-free radical. That's what I called it, and that's on the board. Okay, it's one of several oxygen-free radicals. And 5 says that superoxide dismutase converts superoxide into water. Is that true? What is it converted into?
Hydrogen peroxide.
Hydrogen peroxide. That is not water. Hydrogen peroxide is really dangerous itself. That's why you put hydrogen peroxide on wounds. Right? When you get a cut, one of the ways that you sort of get rid of bacteria is put some hydrogen peroxide on it. Right? Okay. 15. 15. Okay. Which of the following statements about mitochondrial DNA is accurate? So I say the answer is A, and so 2, 4, and 5. What do you say?
I said B.
B. 2, 3, 4, and 5. So we differ on 3. 3 says the amount of DNA in a human mitochondrion is 0.01% of that found in the nucleus. What about that? So every digit is important. It's false because it's what? 0.001. That's 1,000. Okay, not 100. All right? That to me is a big difference. All right, 16, 17, 18, 19. Get your share of them. This is yours. 20. 21. Question about 21? All right, so we're looking at 21. So how much again, we haven't gotten these calculations straight. How much NaCl would you weigh out to make 1 liter of a 33% solution of this salt? That's very, so that's just a percent. So 33% of this salt, and that my note sort of just misled you. The note was of no consequence. Some of you see that? Say, why did he put this note down there? Okay, because we didn't have to use that information. You with me on this? So let's go ahead and do this calculation. How much sodium chloride would you weigh out to make 1 liter of a 33% solution? So if I ask you to define a 33% solution of sodium chloride, how would you define it? 33 grams of sodium chloride
In 100 milliliters.
in 100 mils. And so, wow, it's like I got another problem here. It's like I got another problem. So 33 grams and 100 mils would, and I ask you to make 1 liter, how much would that be? That would be 330.
So it's E.
Wow, this is a second mistake. Second mistake.
Yeah, I definitely did that wrong. I don't know
So
what I did.
if you have E, I'm glad I didn't take this exam. All right, so 21 actually instead of D is E. I don't know what I was thinking. Correct answer.
21 is D?
What'd you say?
Oh, that, okay.
All right, you straight why it's not D?
22 is D. Okay.
Yeah. Now, again, the note was absolutely just a distractor. So it has nothing to do with this calculation when you're making a percent solution. Okay? All right, 22.
I thought it had something to do with small.
23. 24. Your question about 24? Why do we believe that the ancestor cell that it evolved into all components of the eukaryotic cell except mitochondria and chloroplast was similar to thermoplasm?
Histones.
Was this, did I use, did you
I
say
said
something? You just
histones.
yawned.
I said histones.
So the answer is what? You say because
It has DNA binded to histones like today's eukaryotic cells do.
because thermoplasma is the only bacterium that we know of where histones are bound in the DNA. That's what we said. And so we think that the DNA in this large facultative anaerobe actually became the DNA in the nucleus. Right? Did we show the nucleus being formed in that cell?
Yeah.
But the reason, and so we didn't say it was because thermoplasma was an archaebacterium, because it lived and heated. Said it was because it had histones associated with its DNA.
Okay, so the facultative is the overall because of the histone.
That's why we think it's similar to thermoplasma. Why thermoplasma is similar to it, because it has histones associated with its DNA. With it.
That makes sense.
Okay, 25.
Yeah.
25? Okay. So, which of the following statements about glycolysis is accurate? I say 1, 2, and 3. What do you say? So I say E is the correct answer. You say what? You said 8. So there, you say 1, 2, 3, and 4. So we agree on 1, 2, and 3. We disagree on 4. So 4 says, in an anaerobe, fermentation is necessary to regenerate ADP. in order for glycolysis to continue.
You'd regenerate NAD.
What did you say?
You'd regenerate NAD.
So it regenerates NAD plus, right? Not ADP. You with me on this? Okay. 26. 27. 27? All right, so let's do this. So I say that E is correct, 1 and 3. What do you say? A. 1, 3, and 5. So again, we always differ by just one. Okay, and that's the problem with these K-type questions. That means you have to know everything in detail. So 5 says, okay, the question is, in which of the following ways would the large prokaryotic ancestor of the eukaryotic cell have become more competitive with other cells by pinching off parts of its plasma membrane, leading to the formation of intracellular organelles? 5 says its surface to volume ratio would be reduced, making it more efficient in carrying out its function.
It's not reduced.
That does not even make any sense, right? If your surface to volume ratio is going to be reduced, how are you going to become more efficient? We want your surface to volume ratio to do that. You know, we've been trying to do what? We're trying to increase it, okay? That's serious. We're trying to generate some membrane, right, current without changing the volume. Okay, 28, 29, 20. We're looking at what, 29? 28, okay? So which of the following statements about histones is accurate? I say 2 and 3. What do you say? 2, 3, and 5. 5, histones bind to DNA primarily, principally by hydrogen bond. What did I say? So what is the charge of a histone, net charge? What's the net charge of DNA? Don't need to talk about any hydrogen bonds here. You know, it's ion. Yes, sir.
That's a B.
A little bit louder. You said
That's a
B. 2, 3, and 4. So you think that 4 is correct. Histones are synthesized in the nucleus of a eukaryotic cell. What about that? What did you say, Jeff? So no proteins are synthesized in the nucleus. Where are they synthesized?
In the cytosol,
And so how do we get them into the nucleus?
the nuclear pore,
Right? We have to transport them into the nucleus through, what did you say?
the pores.
Nuclear pore. Okay? No proteins are synthesized in the nucleus. All right? Okay. 29. 30. 31. 32. 32? Is that you? All right, so another one of these K-type questions. I say 1 and 4. What do you say?
I said 1, 3.
All right, difference is 3. So which of the following molecules included by the human mitochondrial genome? You say 10 molecules of HNRNA.
No.
Now, we never said that HN, that's heterogeneous nuclear RNA. That's another name for the primary transcript. Okay? That's not made in the nucleus. Oh, I'm sorry, in the mitochondria. Any other questions about that? Okay, 33, 34, 35, 36, 37,
36.
okay, 36. So the primary transcript of a protein coding gene in prokaryotes is blank, while the primary transcript in eukaryotes is what? So what is the primary transcript in prokaryotes? It's the message. You don't have to do any processing. So the thing that is transcribed initially is the final message. What is the primary transcript in eukaryotes? What did you say? So pre-mRNA. What's some other names that we call it? Primary transcript. What's another name that we call it? Heterogeneous nuclear RNA. Okay, but the point is that that's not the final product. We got to modify that in several ways. Okay. All right. 37. 38, 39, 40, 41, 42, 43, 44, 45.
45.
All right. 45. All right, so cell type A and B are both spherical cells. Cell type A has a diameter of 0.25 microns and cell type B has a diameter of 11.3. How much larger is the volume of cell type B than cell type A? So did anybody else get B? 90, did you get a number? What numbers did you get?
2,160.
You got 92, 160. What did you get, Corey? You got 92, 160. You got 92, 160. So now that is close enough to 92, 492. Okay? Now maybe my calculator is batteries may need to be charged or something. Okay? But you know, a number of you asked me about that, and I said, yeah, that's close enough. Okay? So now, what is the formula what's the simple formula that we decided to use for this? It's just that simple. We divide R by R. That's real easy. Okay, so the answer is B. And again, we don't have to go through that. Just check with somebody who did it for you. But 46. 47. Now let me just, Aaron Marks just came in. You guys know Aaron?
Mm-hmm.
Take a look in the back. Aaron was the tutor in this course for probably 3 semesters. So Aaron is a senior. He's been accepted at a number of medical schools, University of North Carolina, Chapel Hill. You haven't been accepted at Duke yet, have you? Where else have you been accepted? Case Western, which is a very good medical school. And where else? Howard. East Carolina. Okay, so Aaron is one of our top seniors, graduating seniors, who's done very well here. And that's the product of all of his efforts. Okay, let's finish this up. 47. Is that where we are? What number are we on? 47? 48? 49? 50? 51? 52? Okay. Now, I've seen one of you about this exam. What I've said is that if you didn't pass the exam, you need to make an appointment to come in and talk to me. I think I can help you. Okay? Now, we've got 5 minutes. What would you like to do? I'm just trying to work with that.
Oh no.
You know, this is the thing that's very interesting about this class is that you absolutely refuse to talk to me. And I think this is a sign that the age difference now, and this is, I'm telling you, I should really retire. The age difference is so great that I don't know how to talk to you now. Because I keep talking the way I've been talking for years, you say absolutely nothing to me. I want to draw mitochondria on the board. Okay? I'm compelled to do this. Especially with my good friend Jeff Andrews out there, because I know he has some questions. So he likes to ask questions when you guys don't like to ask questions. So let's talk about the third step now in the transport, just in a couple of minutes, of mitochondrial precursor protein into the mitochondria. Okay? Third step. So this is all it is. So here's our mitochondria, and I'm just going to draw one contact site. I don't need to draw 3 of those anymore. So here's one contact site. And so let's just put maybe 1 crispin, because I need some room here. 1 crispin. Okay, now here's Tim. Here's this channel in the inner membrane. I'm gonna make it large. This channel's about this large, actually. So that's 10. And now 10 is arranged so that it's basically on top of Tom. Here's Tom. And so here's the receptor part of Tom that actually bound initially the signal sequence. Okay? So, now the interesting thing that we talked about before is that the inner membrane has a membrane potential, and we're going to come back and tell you a beautiful story. So this membrane potential is created by electrons being transported along the membrane, resulting in the transport of protons across the membrane. So we create a proton gradient across the inner membrane. I'm going to come back and talk about that later. And that proton gradient actually is what's responsible for the difference in charge. If you move protons which carry a positive charge from one side to the other, you're going to leave an excess of negative charges on one side, and you're going to have an excess of positive charges on the other side. So that is the basis of this membrane potential. So the inside of this membrane now carries a net, and we're going to talk about this potential in much more detail. So there's a pH difference across this membrane, right? Because there's a difference in proton concentration, okay? And that's what creates this potential difference. So it's plus on the inner membrane side, it's minus on the matrix side, okay? And so what we've said is that this is responsible for driving now the signal sequence into the matrix, okay? So here's the signal sequence now, this amphipathic helix having actually entered the matrix. Here's the rest of the proteins that are sort of curved. So we still have proteins bound to it out here that are keeping this from folding. Now the next thing that's really interesting is that once the signal sequence pokes through, HSP70 binds to it and actually undergoes a conformational change. It binds and undergoes a conformational change, binds, and so it sort of winds it in. Okay, so that's the next force that's sort of pulling this in. So HSP70, and so we're going to have to come back and really try to figure out how HSP70 works. So here's HSP70, and it's actually part of a complex, but the main actor seems to be HSP70. So this is HSP70 that's part of an import complex. Okay? So we're going to say that this is part of a import, and I'm going to call this import ATPase complex. And so it turns out that HSP70 is an ATPase, and so it is energized by the hydrolysis of ATP. Okay, so ATP, we're going to use ATP for this to sort of wind it in. ADP plus PI. Okay, so the membrane potential now is no longer, we've essentially gotten the signal through 10, and so we need something else to continue to move it in. Okay, let's go ahead and take it in. Let's take another minute. So here's the protein now that we moved all the way in it. Here's the terminal sequence. Here's C. All right. So we've transported. This is the way we transport a matrix protein into the matrix. And what I told you before is that we're now going to cut the signal sequence off. So there's an enzyme in the mitochondria, and I tend to draw these as PATN. So this is a signal peptidase. So the signal peptidase is now going to cut the signal sequence off because it's already done its thing. We don't need it anymore. Okay? So we're going to actually produce the signal sequence now. And here's the rest of the protein. And so what we've done now is you create a new N-terminus. And that N-terminus is not necessarily methionine. So the methionine is right here. Okay? So here's the new N-terminus on the polypeptide chain. Here's the C-terminus. And now we're going to fold this polypeptide in conjunction with chaperones. Okay? Chaperones, and we may come back and talk about this in a little bit more detail. It involves HSP60 as well as HSP70. And now here's this protein. This is the mature polypeptide chain. So we're precursor here. We've now cut off the N-terminus, internal sequence, and this is now the mature mitochondrial protein. Now, the final statement before we leave is that, again, this is how we make a matrix protein. Now, the point that I'm making is that to get into the matrix, you only need one signal. To get into the inner membrane, you need actually two signals. Okay, now just the final point is that the enzymes in the citric acid cycle are in the matrix. Okay, so this could be one of the enzymes in the TCA cycle. Okay, so citric acid cycle enzymes are in the matrix. And so this could, and there are a bunch of other proteins in the matrix, but we're just saying that this could be how one of those citric acid cycle enzymes gets into the mitochondria, in the matrix. So we also call this the TCA cycle. Is there another name for this? You guys do this before? TCA cycle? You do that in general biology? No, the Krebs cycle.
The Krebs? Oh.
Krebs cycle. So, citric acid cycle, TCA, all of those things are in the same thing. Krebs cycle. Okay, so I finished this story. I might come back and show you how we actually do an inner membrane protein. Okay? This is how you transport a matrix protein from the cytosol into the mitochondria. We straight on this? Okay. Now again, when we come in on Friday, we may have a pop quiz that would cover this and what we did last time. Okay? All right. Until then. Oh, Aaron?
How's your Saturday meeting? So tomorrow at 10 p.m., Harvard Middle School is coming in, and we're also having one night meeting coming up.
So the Health Korea Society meeting tomorrow at what time?
7 p.m.
Right here. Okay.